Hey everybody, what's up? So we've been learning about the layers of the earth and how the earth is put together. And that's important because it helps us to understand about the changes that we see on the earth. And we see lots of changes on the earth because partly of the composition of the earth and the layers of the earth and how they're put together, but also how those layers, things like the convection currents in the mantle, affect the crust and how that crust shifts and moves around because of those convection currents. And so we're launching into now studying plate tectonics, which is this conversation about parts of the Earth's crust that move around as a result of the convection currents on the mantle layer of the Earth, and how those result in changes on the Earth's surface. So let's check out plate tectonics. So about 175 million years ago, this is what our Earth looked like. We didn't have land on the other side of the Earth, from what we can see here, like we do today. It was all just one big glob here on the Earth. And then there was just water everywhere else. 175 million years ago, considering the 4.5 billion years of the Earth's age, is not a very long time. How is it possible, though, that in that short period of time, massive continents would separate and move apart? And then also just are they still moving? So we're going to talk about those things today. A couple of key terms you need to know. So plates are these large pieces of the Earth's crust that sit on top of the mantle. Plate boundaries are where two plates meet. And then plate tectonics is this idea that plates move around on top of the mantle. So we can see the different plates here separated by black lines. These are the boundaries, the plate boundaries, these black lines. And we can see some of the plates are really big, like the African or Eurasian or North American plate. Pacific plate's pretty big too. Some of them are pretty small, like the Arabian plate, the Caribbean plate, the Cocos plate. How about the tiny little Juan de Fuca plate? This is actually off the coast of Washington and Oregon State and a little bit of Northern California here in the U.S. So lots of different sizes. The Antarctic plate is the biggest plate. And these black lines denote the boundaries, or the places where the two plates meet or several plates meet. Go ahead and check out this cool video in your slides called What Causes the Continents to Move. This gentleman from Scotland talks about how the continents move and how that's a result of the magma layer of the Earth. So go check that out. When we have continental movement, we get different features on the surface of the Earth. And one of those features is a mid-ocean ridge. So a mid-ocean ridge is on the floor of the ocean or the ocean bottom, the oceanic crust. The oceanic crust or the ocean floor is not just flat and sandy. It has volcanoes. There are earthquakes that occur there. And it will have long stretches of mountains called mid-ocean ridges. You can see an example of a mid-ocean ridge here. You can also see how mountains are created in the ocean as well from volcanic activity. And in both cases, we can see that this is a result of volcanic activity. Mid-ocean ridges are a result of either plates pulling apart and separating, as these arrows indicate, and lava seeping up and outflowing and piling up and creating an ocean ridge, or possibly maybe an upwelling of lava due to maybe some sort of dissolved crust that's coming in from a subduction or something. That creates a seamount or a sea volcano, and we get a pileup of lava there from that volcanic activity. So when you have lots of volcanoes together, or you have a really long stretch of this divided, separated crust, you'll call that a mid-ocean ridge or an under-ocean or ocean floor mountain range. The ocean floor has lots of mid-ocean ridges. Anywhere you see black lines, these are mid-ocean ridges. And this is in the Pacific Ocean here. Here we have South America, Central America, North America. Over here is going to be Hawaii. This is going to be like Asia and Indonesia, okay? And this is a mid-ocean ridge through the Pacific Ocean. Okay, over here we have another one, quite big mid-ocean ridge called the Mid-Atlantic Ocean Ridge. This is the Atlantic Ocean, okay? And we have smaller mid-ocean ridges throughout And a lot of these ocean ridges are along plate boundaries because we have separation of plates in those areas, or divergence. We'll talk more about that later. Underwater volcanoes have a whole different life cycle. And if you click on this link in your notes in the Canvas slides, it'll take you to a place where it'll talk about some underwater volcanoes. Pretty cool stuff happening there. I wouldn't miss that video because it talks about, this is the newest, little GIF of the newest underwater volcano off the coast of Tonga. It's pretty explosive, and I don't mean that as a pun, but it is kind of a good pun. We can see underwater volcanoes with heat sensors show up as red, and we can see underwater volcanic activity showing up as red in underwater volcanoes when we do heat sensor technology to look at the ocean floor. How about seafloor spreading? This is one of the culprits of a mid-ocean ridge. We would find the youngest rocks on Earth at seafloor spread areas or mid-ocean ridges due to seafloor spreading, because this is what happens when we have plates pulling apart and lava seeping up in the gap that forms. It is lava that comes up and then hardens into rock. And so those are brand new baby rocks. They are the youngest rocks on Earth. The oldest rocks, on the other hand, are found in the middle of continents, in the middle of Earth crust, right? So some of the oldest rocks are the Appalachian Mountains. That is one of the oldest mountain ranges in the world. It is several billion years old, and it is in the South and Midwest of our country, in places like North Carolina, Tennessee, Virginia, the Appalachian Mountains. So we would find the oldest rocks in the middle of the continents, and the Appalachians is an example of that. It's not the only one, but it's a good one. Here we can see actually all the gray is continental crust or earth crust. These are continents: North America, Central America, South America. We can see Africa here. This is Europe, and going into India and Asia, China. Up here is Russia, Siberia, right? So the rainbow kind of areas are areas that show volcanic activity and seafloor spreading. So anywhere it's super dark red, these are areas where the seafloor has spread. And if you were to compare that to our previous slide showing mid-ocean ridges, you can see that these black lines that indicate mid-ocean ridges are shown here with thermal photography as red lines. And that's because we have new volcanic lava seeping out of those areas. So we can tell from our thermal imaging of the ocean floor that those red areas coincide with our mid-ocean ridges. And so these are young, hot rocks that form from seeping lava due to seafloor spreading from plates pulling apart. Okay, and by plates, I mean plate tectonic plates. Seafloor spreading is where we find the youngest or newest rocks on mid-ocean ridges, and older rocks are pushed outwards. And we can see that here where we have plates pulling apart, right? You can see the arrows show the oceanic crust pulling apart in opposite directions, creating a gap for magma to seep up in, and that magma spills over and forms new rocks. And if that's happening under the ocean, then we see the formation of a mid-ocean ridge. Go ahead and check out Bill Nye on this video in your slides on Canvas. Slide number 13 has a cool video by Bill Nye about seafloor spreading, and he kind of shows you some places where seafloor spreading is happening, and you get to see some actual footage of seafloor spreading. And it's pretty cool because you get to go underwater, see what it looks like. So check out that video on Canvas in your slides. So if the seafloor is spreading, we have the ocean bottom getting bigger. Does that mean that the earth is getting bigger? Like it's getting fatter and bigger around? No, that's not happening, because we have another activity happening due to plate tectonics called subduction. And subduction is this process of recycling the older Earth's surface back into the Earth's upper mantle. So we have plates that actually dive down underneath other plates. They kind of layer down underneath. And when this happens, there'll be, this is oceanic crust diving down underneath continental crust here. And as that happens, the water that is in this layer of oceanic crust actually heats up and boils and turns to steam. And when that happens, it melts all of this rock underneath here and it sends it upward because of convection currents. And as that melted rock moves upward, it creates what's called a volcanic arc. We have a really good example of this in the Cascade Mountain Range that goes up Northern California and into Oregon and Washington State. It is due to the diving or subduction of the Juan de Fuca plate underneath the North American plate. We have a bunch of volcanoes, Mount Shasta, Mount Rainier, Mount Hood, Mount St. Helens, that are a volcanic arc that has formed as a result of subduction and those plates colliding and having that Juan de Fuca plate subduct underneath the continental crust of the North American plate. We can see these plates here are moving in lots of different directions. The red arrows at the boundaries of the plates indicate direction of movement. Sometimes you see them pushing in on each other. That's where we see things like subduction, where we see plates pushing in on each other. Sometimes we see them pulling apart, like here, between the Cocos plate and the Nazca plate. That's where we might see seafloor spreading or mid-ocean ridges with young new rock. So maybe some volcanic arcs here with one plate going underneath the other. Maybe some seafloor spreading, lava seepage, and mid-ocean ridges here. And we can have plates just kind of go past each other, like this Coco plate is going up and the North American plate is going down, and that's creating actually the San Andreas Fault, which is a whole nother conversation. But that's what happens when plates rub up against each other. You get fault lines and earthquakes. So all of these plate boundaries they have their own name, and you do need to memorize and know them. They're important because they represent different changes that we see on the Earth's surface. We see different types of changes with the different plate boundaries. So when we have divergent plates or plates that are pulling apart, we see things like seafloor spreading and that volcanic seepage with mid-ocean ridges. When we have convergent plates, we have what's called mountain building. And we get that subduction sometimes, where we get volcanoes building, or we might just see them crash into each other. We don't have one subducting underneath the other. We just have them bunching up, kind of like a bunch of, like if you rubbed up against a carpet, or like not a carpet, but a rug on the floor, and you bunched it up into a ball. That's sort of what can happen at convergent plates as well. And we end up having what's called mountain building. And we can experience earthquakes in that situation. And then we have transform boundaries, where one boundary pushes past the other boundary. And from there we get earthquakes. And we see this with the San Andreas Fault in California, which is the large fault in California that creates a lot of the earthquake activity in California. So hopefully now you can answer this question in your guided notes. What earth change or geologic feature could result from the movement of each one of these plate boundaries, and why? What would you see at transform boundaries? What would you see at convergent boundaries? And what would you see at divergent boundaries? The San Andreas Fault, like I said, is a fault that is formed because of transform boundary movement. We have the Pacific and Cocos plates moving to the north. We have the North American plate moving to the south. And as they push past each other, we have fracturing or breaking of the both the oceanic and the continental crust. And we end up with all kinds of different formations. Sometimes we can see mountain ranges. Sometimes we can see big, deep cracks in the ground as a result of this. But we definitely will experience heavy-duty earthquakes from this. Think about what that means for California over time as this plate begins to move up with a big part of California and this plate moves down. with another big part of California. This cool video is by National Geographic. You can find it on slide 19 of these slides. It's about the biggest earthquake to ever happen in California as a result of the San Andreas Fault. You probably want to go check it out. Another cool video to check out is a video about volcanoes that occur because of divergent plate boundaries. And remember, divergent plate boundaries is when we have plates that are pulling apart or away from each other in the opposite direction. Finally, let's take a quick look at that supercontinent that originally was all in one place on one side of the world. That supercontinent is called Pangaea. And this is where all the continents were once connected together. But because of plates moving along on convecting currents on the magma of the magma Earth's layer, or the mantle of the Earth's layer, we see the continents that we have now. But you can kind of look at the continents we have now, and you can see how Pangaea was all connected before all of them drifted apart to their current locations today. So let's talk about 3 pieces of evidence that we have for Pangaea, an important thing for you to know for a test or a mastery check. 1, the shapes of the continents all seem to fit together like a puzzle. That's big evidence for Pangaea, definitely confirming evidence for Pangaea. 2, we see fossils of the same organisms that are found on separate continents. For example, we see fossils and evidence of marsupials in Brazil and in the Amazon forest. That's pretty crazy, because the only other place that we see marsupial fossils, and that we actually see current day fossils, or not fossils, current day animals that are marsupials, like kangaroos, wallabies, and koala bears, is on the continent of Australia. So Australia and South America are really far apart from each other, like a vast ocean distance apart. There's no way these animals could swim or fly that distance. And so the only way we can think of that we would have marsupials on present day Australia and fossils that match those marsupials on present day Brazil and the Amazon rainforest would be if some point those continents were touching each other, and those animals could move from one place to another by walking or transporting that distance. So those fossils are evidence of Pangaea and the fact that those 2 continents at one point were right next to each other. Finally, the 3rd piece of evidence that Pangaea existed and that continents were once upon a time all together in one big massive supercontinent is that we know continents are still moving today. They're moving very slowly. In fact, if one moves an inch in 1 year, we say that's fast for a continent. Doesn't feel very fast to us. If you only moved an inch in 1 year, you would be extremely lazy, worse than a sloth. But the continents are moving, and we have lots of evidence of that in earthquakes, mid-ocean ridges, mid-ocean trenches. We have subduction with volcanic arcs and mountain building. So we know that these continents are still moving, and they could potentially even maybe one day create another supercontinent. A couple of years ago, one of the largest earthquakes that ever happened in our Earth's youngest mountain range, which are the Himalayas, just on the border of Nepal and Pakistan. And this particular movement was indeed an inch in one earthquake. That is a huge amount of movement for a continent, but we were able to measure that movement because it moved so quickly and so much in such a short period of time, just a minute or so. So we know that these continents are still moving. All 3 of those things argue that Pangaea once upon a time was on this earth, and that potentially we could see something similar to that again, maybe in another 100 million years. Go ahead and answer the questions on your notes. I know this was a long one today, but we had a lot to talk about. I hope you listened to all of it and learned a lot. It's pretty interesting stuff. Maybe I'll play a music video for you about it as the time goes on. Turn in your notes and have a great day.